My name is jihyeok. I will introduce signed networks in social media. In this work, authors aim to analyze the signed networks. Specifically, they explain properties of signed networks using two different theories. The one is structural balance theory, which was introduced earlier in the field of social psychology, and the other is status theory, which is developed by authors. Previously, there were bulk of research which largely aims to explain exclusively the positive interaction between users, that is, connecting people to their friends, fans, followers, and collaborators. But in many settings, it is important to explicitly take negative relations into consideration, especially when studying interactions in social media. In social media, there can be disagreement as well as agreement, and enemy as well as friends. To this end, it is very important to inspect signed networks in which both positive and negative interactions occur at the same time. They used triad, which is the set of three nodes with signed edges, as basic unit of analysis. Four different triads can be constructed. They explored those triads using the two theories. First, in the field of social psychology, researchers tried to explain plausibility of each triad by introducing structural balance. Assumptions and the following constructions of signed networks are listed. As a concrete example, let's look at a configuration located in top left corner. Suppose there were already two edges, the one positive edge between A and B and the other positive edge between B and C. Using intuitive assumption that the friends of my friend is my friend, we can expect there is a positive edge between A and C. The other kinds of triad can be explained similarly using different kinds of assumptions. With assumptions listed in previous slide, we can conjecture plausibility of each type of triads. Previously, social psychologists called triads are balanced when those triads satisfy previously presented four assumptions, and they thought balanced triads are plausible and unbalanced triads are implausible. For example, since a friend of my friend is my friend, triad type 3 is balanced and hence plausible. On the other hand, since enemy of my enemy is my friend, triad type 0 is unbalanced and hence implausible. Briefly, when the number of positive edges in given triad is odd, then the triad is balanced, hence plausible. And the number of positive edges in given triad is even, then the triad is unbalanced and implausible. A third variant of structural balance theory called weak structural balance was introduced. The only difference is that in notion of weak structural balance, there is no assumption about the enemy of my enemy. Therefore, triad type 3 is still plausible and triad type 2 is still implausible. In contrast, since there is no assumption about enemy of enemy, there is no prior reason to favor one of type 1 or type 0 over the other. With experiments over large-scale datasets, they found that weak notional balance explains signed networks better than original notional balance. Authors developed novel theory called status theory, which afterward be revealed to be better explanation compared to balance theory over directed signed networks. In status theory, the meaning of sign of edges is different with in balance theory. In balance theory, sign of edges indicates likes or dislikes. On the other hand, they used sign of edges as indicator which represent relative status between nodes. For concrete comparison of different outputs which came from different meaning of sign of edges, Suppose there is two positive edges, one between A and B and the other between B and C. In structural balance theory, we can expect the edge between A and C to be positive. In contrast, with status theory, because of transitivity, we can expect the edge between A and C to be negative. In addition, while structural balance theory naturally expects edges in networks to be undirected, directed networks are more feasible in settings of status theory. Indeed, they found that in undirected settings, balance theory explains observations better than status theory, and conversely, status theory explains better on directed networks. They used three different kinds of large-scale datasets to analyze sign networks and evaluate two different theories. Statistics of each dataset and meaning of signed edges are listed above. As introduced, the meaning of positive and negative signs are different across these settings. With different kinds of usage of sign, we can analyze networks in more diverse form, hence evaluation on two different theories will be more reliable. They explored those datasets with various settings. They compared structural balance theory with weak notion of balance using settings of undirected networks. They compared status theory with structural balance theory using settings of evolving directed networks, where the networks not only have directed edges but also evolve over time. I will introduce those analyses on various settings step by step. First, they compared structural balance theory with weak notional balance. Notions they used for evaluation is listed in Table 2. They calculate prior probability of triad type T. First, we shuffle the signs of all edges in the graph, keeping the fraction of positive edges the same, and then the prior probability of triad type T is expected fraction of triad type T after shuffling. If empirical probability of type T is larger than prior probability, then we can say that triad type T is overrepresented relative to chance. Conversely, probability of type T is smaller than prior probability, then triad type T is underrepresented relative to chance. For example, applying structural balance theory into those configurations, since type 3 is balanced, therefore plausible, empirical probability of type 3 should be larger than prior probability, hence overrepresented. They also introduced the notion of surprise. Surprise is the number of standard deviation from expected number of triads under random shuffling. Magnitude of surprise indicate how significant over and under representation is. For type 3 and type 1, original structural balance theory seems applicable. Type 3, which is balanced, is overrepresented as expected. In contrast, as type 1 is unbalanced, type 1 is underrepresented over all datasets. However, there are disagreements over three datasets for triad type 1 and triad type 0. Since type 1 is balanced, those triads should be overrepresented, and since type 0 is unbalanced, they should be underrepresented. But in Slashdot dataset, type 1 is underrepresented, and both in opinions dataset and Wikipedia dataset, type 0 is overrepresented. Therefore, original notion of structural balance cannot explain all kinds of observations over different applications. On the other hand, weak notion of balance can be applied to all types of triads. Since the theory does not presume assumption over two common enemies, both type 1 and type 0 triads are plausible. They also argue that the results are statistically significant as magnitude of surprise is very huge. For second analysis, they explore settings of evolving directed networks, where the networks not only have directed edges but also evolve over time. By making status of networks time-dependent, we can compare which models among two different theories are more applicable for predicting future status of networks given incomplete observations. They introduced notion of baseline over two different point of view. Some users produce links almost exclusively of one sign or the other, while others produce relatively even mix of both positive and negative links. Therefore, we should measure baseline to neutralize different biases of each users. They first introduce a concrete example called joint positive endorsement. There can be situations where both A and B already have interactions with third node X. Suppose node X assign positive edges to both A and B. Given this observation, how should we predict the sign of the edge from A to B? Structural balance theory naively expects the edges to be positive since the friend of my friend is my friend. However, empirical observations are not that naive. In real datasets, the link that is produced in this situation is more likely to be positive than the generative baseline of A, but at the same time less likely to be positive than the receptive baseline of B. First, they introduced a real-life example to explain status theory. Suppose we were to interview the players on a college soccer team. Now we can construct directed graph based on the answer. If A thinks skills of B is better than of herself, the edge generated by A will have positive sign. With this notion and adapting third node X, we can think joint positive endorsement situation with two different point of view. First, with generator A's point of view, since B already assessed as highly skilled player by X, A also expect B to be highly skilled player. Therefore, generator A will more likely to give positive assessment than the generative baseline of A. Second, with recipient B's point of view, since A also assessed as highly skilled player by X, B expect the generator A to be highly skilled player. Therefore, recipient B will less likely to be assessed positively than the receptive baseline of B. By considering two different point of views based on either generator or recipient, status theory can explain joint positive endorsement situation. For further analysis, authors introduced more notions. We denote contextualized link, briefly C-link, to be a triple ABX, with the property that a link forms from A to B after each of A and B already has a link either to or from X. Specifically, there can be 16 different C-links possible. They also define generative baseline and receptive baseline of C-link type T, as well as generative surprise and receptive surprise. Generative baseline is a summation over generative baselines of all nodes AI, which means the expected number of positive edges we would get if we let each AI BI link form according to the generative baseline of all nodes AI. And generative surprise for type T is the number of standard deviation by which the actual number of positive AB edges in the data differs above or below this expectation. Further, they incorporated the role of status. We first assign the node x as status of 0, then if x links positively to a or a links negatively to x, we assign a status of 1. Otherwise, we assign a status of -1. With those notions, we say that the generative surprise for type T is consistent with status if these status have the same sign as the generative surprise. Similarly for receptive surprise. Now we can analyze networks using four different theories. Theories are listed above. The result shows that status theory explains observations better than structural balance theory does, where status theory is consistent with generative and receptive surprise for much larger number of types of total 16 types. They, they also analyze the reciprocal configuration at which user B create a link to A after A create a link to B. They called newly created link as a reciprocal link. With structural balance theory, reciprocal links should have same sign with original link. In contrast, in status theory, reciprocal link should have opposite sign with original link. Result shows that when original link was positive, then structural balance theory are more plausible than status theory. However, if sign of original edge was negative, then a hybrid of two principle was needed. Furthermore, they inspect connection between structure of networks and the sign of edges. The general conclusion is that the positive edges tend to occur in clumps, while negative edges tend to span clusters. Uh, we must first define embeddedness. Embeddedness is the number of common neighbors that its endpoints have. Edges with endpoints having fewer than around 10 shared neighbors tend to be negative. However, as an edge participating in more triads, it tends to be increasingly positive. That is, a link is significantly more likely to be positive when its two endpoints have multiple neighbors in common. They analyze network in the settings of all positive and all negative networks. All positive network is the subgraph consisting only of positive links. Definition is analogous for all negative networks. I listed a few definitions which require to interpret the result for evaluation. They made baseline for comparison using random shuffling. Firstly, we randomly shuffle the edge signs in the full network and then extract the all positive and all negative networks from this shuffled version. All positive networks have significantly higher clustering than their randomized counterpart. This, uh, uh, this observation further reinforced the general conclusion as we discussed in the beginning. However, results on components seems to be counterintuitive. They provided alternative explanations. A giant network in the real dataset tends to consist of densely connected clusters linked by less embedded ties. However, all positive networks have dense clusters without the bridging provided by less embedded ties, while all negative networks lack a sufficient abundance of dense clusters to sustain a large component. In summary, they provided empirical results using extensive experiments over large-scale online datasets for different settings. At the same time, they compared the two different theories to explain structure of sign networks. First, balance theory was reasonable approximation to the structure of sign networks when they are viewed as undirected graphs. While status theory better captures many of properties when the networks are viewed in more detail as directed graph that grows over time. Second, a link is significantly more likely to be positive when its two endpoints have multiple neighbors in common. Those observations and explanations they gave was very interesting. Thank you for listening.